Okay, so hello everybody. So let us start the discussion. And so this, what I have sketched here is the plan, and some of these discussions will happen like chalkboard type, and some probably I will have to go back to slide types. But let's see how it progresses. Let me first motivate you why you should know how to observe in radio astronomy. As in the last session, if you were there, and Poonam pointed out all these different things that goes into imaging and the convolution. And you had asked several questions, which were aimed at the point that do we actually make an image of the sky, or we make an image of what we want to see? Because the imaging process itself is so complicated. Not only imaging, but even the calibration you will see is so complicated that at some point.
So, Prasun, sorry to interrupt you. Do you have a better mic? It seems like some noise are there in the background.
Let me switch off the fans. Can you hear now? Is it better, or I can change to a bit different mic then?
Yes, some noise are still there.
Okay, I'll change to a different mic. How is it now?
Yes, it is better. It's definitely better.
Okay, so now it is difficult for me to hear. Okay, can you speak a little bit, Raghu?
Yes, it is definitely better.
Okay,
yeah, I mean, no noise now. Okay, good. Go ahead.
Fine. So let us start. Start again. So the calibration and imaging deconvolution process can introduce a lot of unwanted and unknown errors. And what you may end up getting is that say you see that you have observed a dinosaur in the sky and try to interpret that there are dinosaurs in the sky at redshift of 6. And then at the end of the day, when you do a little bit of better data analysis, you may figure out it was an owl instead of a dinosaur. So the point is that even if you are a theorist, pure theorist, you need to know how to interpret the data that you get out of these telescopes. Otherwise, your theory will not be able to aim the questions properly. So in astronomy, particularly this, observing the EOR signal or detecting the fluctuations of hydrogen as it's progressed from the cosmic dawn to the reionization to the post-reionization era, you are not, you don't have a choice to be a theorist or an experimentalist. You need to be an astronomer. Okay, so that is the motivation of why we need to learn how to do radio astronomy, because unfortunately the signal is in radio, right? So the plan of the lecture is this, and it will kind of mirror what Poonam has been talking about apart from the last lecture. But you will see that we'll discuss different things and we'll build up on the sketch that we already have after 4 lectures by Poonam. The first lecture will rediscuss the signal that comes from the source to the receiver. And we'll see that many things happen to the signal as it comes from the source to the receiver. And that's the lecture now, today. And many of those are ignored in conventional radio astronomy, but are very important when you come to detect signals like EOR signal or redshifted 21 centimeter signal. The second lecture, once you receive the signal, what do you do with it? So you get the visibilities and what type of informations those visibilities contain, and what you can do, what you cannot do. So that's what we'll discuss in the morning lecture tomorrow. And in the afternoon lecture, we'll again go through gain and calibration, and you will see that there are active works going on in understanding this gain and calibration part. Unless you do that, you will never be able to detect the EOR signal, and we will discuss why. Next, the step 4, we can argue that it is not required because all these informations that we need are contained in the visibilities, and you can directly use them to get the kind of intensity mapping that you are trying to do in case of redshifted 21 centimeter signal. But then you will see that, as Raghu was discussing, with the 21 centimeter signal, there comes this foregrounds. And to understand those, you need to do imaging and deconvolution. And that we have to learn again to some extent, to the extent that normally it is not learned, because it's a different ball game when you are observing the redshifted 21 centimeter signal. That's why it has not been observed today, till today. And in the last lecture, we'll see, once you have the visibilities and you have taken care of the foregrounds, you have calibrated it properly, what do you do with it to get the intensity mapping, to get the power spectrum out of the visibility. Okay, so let us start now. And I hope that all of you can unmute yourself. So if you have any question at this point, you can ask and I will proceed. So we'll kind of have like 15 to 20 minutes stretch of lectures, me speaking random things, then you can ask coherent questions. I will give answer and then proceed again. So if you have anything to ask at this point, even before we start, please proceed. Is my voice clear now?
Yes, yes.
Yeah,
It's clear.
Okay. And can any one of you try to unmute yourself and say something so that we know that?
Yes, I can do that. Yes, I can do that. Yes.
Are you a host or co-host?
No. I'm just a regular.
Fine. So let us start. So I assume that you don't have any question right now. So let us start. So before we go into the signal chain in the radio astronomy, we need to understand or recapitulate, if you wish, a little bit of statistics. Okay. So let us say that we are observing some statistics and some principle of electrodynamics. So let us say that we are trying to observe a signal, and the signal is a random signal. All the signal that you observe in radio astronomy are random signals. Okay. So I have a random signal, and the signal, let us call it Y. And it's a random signal, so it's not a function of anything. But I can say that, say this is what is Y is nothing but the time period of a pendulum, and it may be measured by you at different times. So those different measurements are leveling by xi. It may be that different people have measured it, so that also can be xi. It may be that you have used different pendulum of the same length of the string to measure the time period, so xi can be that also. So whatever it is, Y is not a function of xi. If it is a function of xi, I will not call it a random signal. I will know exactly what is Y going to be in the next measurement. But it's something that is different at every measurement. So you can as well call it Yi. Okay. So let's ask the question that, and as I said, that all the signals that you observe in radio astronomy are random signals. And if the signal is random, where is the information content in the signal, right? You want to get some information out of it. So where is the information content of the signal? So one thing that you may, all of us know, is when I use this curly brackets, not curly brackets, greater than or lesser than signs, it means some type of averaging. Let's not go into what type of averaging, but I can take the average of the signal. So I can call it mu. I can take the, I can square each signal at the signal itself. So y1 square plus y2 square, y3 square, and then average them, and then subtract square of the mean. And what do you call that? You call that this, right? So these, we know that a signal, even if I give you a completely random signal, I can get these two numbers out of it. But let me ask you a question, because you have already introduced to, you have been already introduced to the answer to this question. So let me ask you that can a random signal have any other information other than only these two numbers? If you wish to answer, you can unmute and answer. Anybody?
So higher order terms.
Higher order terms. But
Like
what do you mean by higher order terms? Yeah. So I can have what is called as skewness or kurtosis, which are related to, say, yi cube or average of yi to the power 4, and then appropriately subtracting and normalizing them. But other than that, anything else that you have learned? So the other thing I said, that the radio astronomy, all the signals are random. It's also Gaussian random, which is that which essentially means that all these higher order terms are 0. Okay, so we have been introduced. So let us look at two signals to understand, to get this point home. So I have two random signals, one in the left with blue, one in the right with black, right? If you calculate, go and calculate the mean and the variance of these two signals, the mean is not actually 0 for the right hand signal, but you can subtract a number to make it 0. But the variance for both of these signals are same. Okay, mean and variance of both of these signal, if I shift the y-axis of the right hand side signal a little bit, they will be exactly same. But does these two signals look exactly same to you? It's obvious that they are completely different signals, right? So what can I do to extract statistically the extra information that I have in the extra information that is different in these two signals? Okay, so any answer to that question now says that I have already shown you these two signals. Mean and standard deviation or variance are same in both of these cases. What if so when I am calculating this averages, I'm taking the signal at a given point and doing to the power n and then averaging those numbers. Instead, if I do this, and this you are introduced to at least once in Tapoma's lecture, what we'll call this thing, what this thing is called. I am not using the average at one point. I am taking the value of the signal from one point and taking the value of the same signal from a different point shifted by j, and then taking the average. What is this called? So this is called the
correlation.
Right. So this is called the 2-point correlation function, right? Now you can imagine that if I look at this function of these signals, they may be different, because if I look at the signal in the left hand side, there, what does the 2-point correlation function tells me? If I look at the signal in the left hand side, say I know about the signal at a given point, and I ask the question, what do I expect the signal at the next, in this case, instant of time? So you are doing this pendulum measurement at 12 o'clock, you have done the measurement, and you are poised to do the next measurement at 12:05. 12 o'clock, you have got some 12, say 10 seconds as a time period. What will be the time period at 12:05? Can I predict that? If I look at the left hand side, I have absolutely no way of predicting that, right? Because this points doesn't care about what is the value of the previous point. So what I am really trying to do is to not look at the signal at a given point, but look at the correlation of the signal at nearby points or at a certain distance. If I do this, ask the same question in the right hand side. So you see that if I have measured at t equals to 1 in the right hand side black signal, and I measure at t equals to 2, and measuring at t equals to 1, if I would have predicted that t equals to 2, I will get the value positive, I would be always right. There is a little fluctuation, there is randomness, but at this time scale, 1 to 2, 1 second in this case, the signal still remain positive. So this function, the signal in the right hand side will have different 2-point correlation function compared to the signal in the left hand side. So let us look at those. So basically, if you before you look at, so basically in the left hand side signal, once I have measured the signal up to a certain time, I absolutely have no way of predicting what the next measurement is going to be, apart from saying that it will have this mean value and the value will stay within this number, which is the standard deviation. In the right hand side signal, I have more predicting power. So if it stays positive at 1, at 2 also it will stay positive. Let's look at the autocorrelation function, a 2-point correlation function. So the first signal, which was in blue, if I look at the 2-point correlation function, of course, if I measure the 2-point correlation function at j equals to 0, so if I measure the 2-point correlation function at j equals to 0, what will that give me? Any idea? So this function is a function of j, right? If I measure it at j equals to 0, what will that give me? It will be yi square, right? And yi square will give me back my sigma square. I mean, if you subtract the mean. So that's what I see here, that at j equals to 0, and in this case, j is tau, in this plot, you get a certain value. And after that, there is no correlation. That's why the signal, the autocorrelation function is 0. If I look at the other signal, it's completely different. Yeah, at j equals to 0, you have certain number of amount of correlation. But after that, it doesn't go to 0 drastically. It remains correlated up to certain lag. I call it lag, that j in this case, because it's time, it's the difference between 2 times in the signal in the left-hand side, I call it lag. So you can say that for this particular signal, I have a predicting power up to 2 seconds. Okay, so if I do the measurements within 2 seconds, I can kind of predict what I'm going to get. Okay, so is this point clear so far? If you have any question, please ask, because this will be the heart of radio interferometry, as you will see, and even when you do intensity mapping.
I have a question.
Yeah, please.
Even when the process is Gaussian, why are you getting the? I mean,
yeah. Okay. So good question. So what do I mean by that? It's a Gaussian random signal. It means the following. So what is the definition of a Gaussian random signal? Asif, you can mute yourself. You can unmute when you want to speak. Okay. So the meaning of a Gaussian random signal is like, so here initially I did 1-point correlation. Then initially I did y average. Then I did y square average. Then I did y cube average, y to the 4 average. Similarly, here I can also do like yi plus j, yi plus k, etc. Right? I can take y from 3 different points and average them. This will be a function of obviously ij, can be a function of ij and k. So this will be called a 3-point correlation. A Gaussian random signal is one for which any point correlation when the number of points is more than 2 is 0. Okay, so it can have a 2-point correlation, but any correlation which has more than 2 y's are 0. So this will be 0, this will be 0, this will be 0. So Gaussian random signal is allowed to have this. So if I know this, which if you remember Topuma's lecture, the 2-point correlation function is often called as xi, which is a function of j in this particular case. This quantity, mu and sigma square, gives you all statistical properties of the signal. There is no more statistical property left if it is a Gaussian random signal. Okay. Okay. So let us take this message further, and let's see that. Let's try to use this tool, which I call the 2-point correlation function. And because we are correlating the same signal at 2 different points, it's also called 2-point autocorrelation function. Auto means same. I can have 2 different random signals and try to correlate them, like say y1 and y2. Then it will be called a cross correlation function. And we'll see one type of cross correlation function in our discussion. So let's try to use this and try to see that what information of a signal it can give. And the signal for us, can you guess if I am trying to observe something from the sky, what is the signal? What is the physical quantity that one like to measure? What is the measurable quantity? Okay, so it's the electric field, right? So I'm measuring an electromagnetic wave. I want to measure the electric field of it. And the electric field is a complex number, and it can be a function of where you measure it and when you measure it. Now, the electric field is also, there is not only a single electric field that you are supposed to measure at a given point. You are supposed to measure more, because you know that electric field has the property, the electromagnetic wave has the property called polarization. So I should be measuring 2 orthogonal components of the electric field at each point. Actually 3, because you may not know which direction the signal is coming from. But anyway, so at least 2 orthogonal components you should measure. But in our entire discussion, I will completely avoid the concept of polarization, and I will assume that all the electric field that we are measuring are plane polarized. So I have only one component, and the electric field vector becomes a scalar, and that's the scalar that I have written. Still, it has an amplitude and phase, and the amplitude and phase, so if it is say monochromatic, then the amplitude and phase of this I can write like, all of us know this. It is customary to write in using complex numbers. You really should look at the real part of it. Electric field is real. But anyway, so we know that we use complex number. I'll not go into the details of those. So this is for a monochromatic wave, I will always get this, right? And what is it telling us? It's telling us that, so let's say that I have this point in the space, which is some distance x away from the origin, where I am measuring this electric field. At a time t, can you tell me, once I have done one measurement, and you see that I can have phase also, say phi 0 constant phase. So if I have done one measurement of this electric field at the position x at a time t, if it's a monochromatic signal, and I have done one mistake here, so we should correct. Okay, so it's a monochromatic plane wave as I have written it, so it's all right. You see that if I have done one measurement, I have absolute idea of what the electric field will be anywhere else at any other time, because I have written this electric field in terms of this function. So one measurement will let me know what is that phi 0, and then I can exactly predict what the electric field will be at any other point at any other time. This is a monochromatic plane wave, and I know that it's a monochromatic plane wave, and then I have this property, which means if I ask the question now that what is the coherence time for this signal, the coherence time is infinite. What is the coherence length for this signal? The coherence length is infinite. So I have introduced to you a new concept called coherence. And this is again another very important concept when I do radio astronomy. So let me go through it. What do I mean by this? For a general signal. Okay. So for a general signal, obviously, before I measure, I have no idea what the electric field is. So say the electric field, I just write a general case, which is this. I have absolutely no idea what is the functional form, this electric field as a function of x and t. So what I do, I measure it at x and t, and say I measure it at this time, and I measure it after a certain amount of time. Okay. Now, if I calculate the 2-point correlation function of these two, I am measuring at the same position. So position has not changed between these two, but I have changed the time. I have measured at two different times. And I change this difference in the time, which I call tau, and calculate this function. And you see that I have done an average over here. What does it mean? That we'll discuss in length again later. But let's assume that we have kept on measuring the electric field at the same position. Maybe there is an antenna here, and I'm measuring the electric field at different times and calculating xi t. So what is xi t? It's our 2-point correlation function, right? What will it tell us? It will tell us how monochromatic this signal is. As we said that if I calculate the 2-point correlation function for this, xi t will remain to a constant value up to very large tau, actually infinity. So which means that for a monochromatic signal, the 2-point correlation function assumes a constant value. So the coherence time is infinite. If I consider a signal which we are discussing earlier, a signal like this, the coherence time of this signal, you can say 3 seconds, because after that, the signal goes to 0. So the 2-point correlation function gives you a measure of the coherence of the signal. Okay, is this point clear? Please, again, if you have any doubt, please raise questions now. Any question? Okay, so let me proceed. Yeah, please. Arghyadeep, do you have a question? Hello. I cannot hear Arghyadeep. You may write in the chat also. Okay. Let Arghadeep write his question. We'll just quickly discuss a similar concept, which is instead of doing the exercise, keeping x fixed and 2 different time, I can do the exercise in the following way. Instead of 1 antenna or receiver, I may have 2. And so this is now say x1 and x2. And I have the electric fields measured now at x1 at the time t. And these are complex numbers. The tilde sign tells you that it's a complex number. Now I measure the electric field at x2, but at the same time, and then do the same correlation. Okay, because it's a complex number, you take a complex conjugate and do the correlation, but that's it. So this, what will this measure? It will measure how the signal remains coherent over a certain length, which is x1 minus x2 here. So this is this 2-point correlation function, x1 minus x2. It measures the autocorrelation of the signal, and this measures the spatial coherence of the signal as opposed to temporal coherence, right? So Arghadeep has not written the question, so let me take this a little bit further. So imagine that you have 1 point source over here, okay, and if you, so this is again a point source, and then it's a monochromatic plane, monochromatic wave coming from the point source. The wave is obviously not plane because it's a point source, it's a spherical wave.
Hello.
Yeah, please go ahead.
Yeah, Arghadeep wrote the question in chat.
Okay. We have 2 functions, E0 and the phase term. Let me, okay. We have mentioned that if we measure electric field at a point in the sky, this will help me to predict field values for all x and t due to the fact that I measured once at a given point. You have measured the amplitude of the signal, right? E0 is the amplitude of the signal. Okay. So you are right that you have 2 unknown values. One is E0, one is phi0. Maybe you have to measure it more than once, but that's it. Actually, you don't care about one of, we'll see that what we care about is the relative difference in the phase, not the absolute phase. But yeah, so if you really want to measure 2, you are right that you have to measure it twice to get all the properties of the signal. But if you don't care about phi0, you just measure once, you get E0. Sonia has asked, what is the coherence time for 2 different monochromatic plane waves? Yeah, so you can, I'll not give you the answer, but you can try to calculate this thing, assuming that one of your signal is coming with omega 1 and the other signal is coming with omega 2. Okay, and try to calculate this. So what all you have to do is that you have to write this E at time t with omega 1 in one case, and the t plus tau you have to write with omega 2, and then try to calculate this, and we'll see what you get, right? Okay, so let's come back here. So I have this point source, and this is one of the wave font that is coming to you, spherical wave font. And I've just obviously drawn a section of it. And say I have a few antennas which are placed like this. Antennas can also have elevations. It's not necessary that they are all at the same plane. So I have few of these antennas. Okay. So what I will see is that if I correlate the signals coming from these antennas, then they will have absolute correlation, and I will see that the signal is, I will get the property of the signal, which is related to now how x1 and x2 is distributed. Because remember that x1 and x2 are the vectors which are telling you what are the position of these antennas. On the other hand, if I correlate signals from these, remember that I am doing this correlation at the same time. The signal from the point source will reach at the same phase at different time. So that correlation will not be same as the correlation of the signal that you get on the spherical arc. Okay. Again, you know exactly what will be the electric fields at all these positions that I have drawn. So you can do an exercise where you can write down the electric field at these positions and try to correlate and see what do I get out of correlation of any of these antennas, two antennas, and what do I get if I correlate these antennas which lie on the surface of the sphere. Okay. So what it in turn is telling you that doing this exercise, I will have some idea about what is the constant phase surface of the wave. The constant phase surface of the wave essentially has the information about the structure of the source in the sky. In this case, we took an example of point source, but had it been anything else, you could have got a different wavefront. And if this entire exercise of correlating at two different positions will essentially let me calculate what this wavefront is. So what the radio telescope does is essentially sense this waveform. So it measures different ways what this waveform is. Once you know the waveform, you can reconstruct your sky. Okay, so again, I will pause here a little bit. We'll switch topics now. So this is the basic things that I thought we'll start with. And now we'll go to more in the signal path as we said initially. So if you have any question at this point, please, again, you can ask and then we'll proceed. Okay. So all that I need to know now is that, okay, so Poonam pointed it out that, see here, we are talking about this coherence, etc. We have the luxury of looking at coherence in radio wavelengths because the frequency here is much shorter. It's in megahertz, so maybe a few gigahertz, not more than that. If you go to optical wavelengths, the frequency is 10 to the 14 hertz. And the reason we cannot have an electric field detector in the optical wavelength is because we cannot see the signal at 10 to the 14 hertz. If you think of the best clocks that we have in the computers that you're using, they go up to say 5 gigahertz. Okay. So the radio signal is, optical signal is 10 to the 14 hertz, much greater than 5 gigahertz. So at that signal, I cannot record as a function of time. In case of radio, I can do. And because I can do in case of radio, I can preserve the phase information about the signal. And as you said, as you have seen that the phase information of the signal, let me reconstruct the source in the sky and do a lot more than what an optical astronomer can do. Okay. So with this, let's say that what we are trying to do. So we are trying to detect this electric field. And then you try to know what is the connection of this electric field with the electric field at the source, right? So that's what you want to know. You don't want to know what is the electric field which has come here at this point. Your ultimate goal is to know the electric field where it has originated. So how to do that? Well, optics tells us how to propagate the electric field from the source to some distance. And that's what you will be using, the propagation of electric field. If you have studied Fourier optics, it should be quite home to you. If you have not, if you remember the basic principle of Huygens, which tells you that every point in a source acts as a secondary source of disturbance, looks like a point source. So what all happens is that if I want to measure the electric field here is E, and if I want to measure the electric field here, so let's say E prime, that will be roughly E to the I k d by d, where d is the distance. If I have a point source, I get this. Okay, so that is the basic idea that we will be using. Obviously, we will be writing it down more properly, but that is a basic idea. So any source I will consider as collection of point sources, and then you can integrate over to get the electric field that an antenna will receive. But there are many things that happens between the source and the observer. In the basic radio astronomy school, when you will learn this, you will just start with this. But for the UR type observation, all the things that happens in between are much stronger, and we need to go through them. Okay, so first thing we need to do is to set up a coordinate system. So let us first set up a coordinate system. I'm sorry. What I wanted to do is, okay. So how do I set up a coordinate system? So first we assume for the time being that we have an antenna which has a finite field of view. What do I mean by that? I mean that the antenna cannot see the entire sky. It only see a part of the sky. So when I talk about a sky, the sky is like a hemisphere on top of our head. We may be looking at only a part of this hemisphere. Okay. So that part of the hemisphere, let me draw it here. So this is the small part of the sky that we want to look at. Okay, that's the antenna can see. So this is often, you have heard this term many times, is called the field of view. Okay. What does it depend on? Anybody? What does it depend on? How big is supposed to be the field of view? What decides the field of view?
Solid angle.
Yeah, field of view is the solid angle, this solid angle. But what part of the antenna decides it? What property of the antenna decides how big the solid angle should be?
Effective area.
Effective area, right? So if I call the antenna diameter to be, what should I use? L. Okay, I am not using capital D for a reason. You can see that I have already used it up. So the field of view is about this. Lambda is the observing wavelength, right? So it is decided by, if you are using a dish antenna like the GMRT, it's a kind of umbrella, if you wish. It is decided by the diameter of that umbrella or the dish. Okay. So actually the inverse of the diameter, if you square that, you get the solid angle. Now there is one more important concept, which is the center of the field of view. Okay. And it will be clear to us why I call this by the following term. We call it phase center. And it will be clear to us why I call this as phase center, maybe tomorrow. But that's all right. It's just a name. You can imagine that the name is phase center. And So I denote it by P. Okay. Now, how do I define my coordinate system? So I have the Earth from which I'm doing the observation. And so say this is the center of the Earth, which I choose as the origin of a coordinate system. And anything that is related to the sky, usually you know that very good choice is a spherical polar coordinate system, because if I consider the source is at a certain distance, then it's all lies on the top of that sphere. So there is this natural spherical geometry. So I will consider this as a spherical polar coordinate system. For the time being, we also do another assumption, which is that all the radiation that we are talking about is coming from the inner surface of this hemisphere. Okay. All the radiation is coming from the inner surface of this hemisphere. It is not that there are several hemispheres and there are radiation coming from different layers in the several hemispheres. Okay. We will see that if the radiations which are coming from the several hemispheres can be just added up, then at the end of the day, when we'll do the calculations quite ahead, we'll see that it doesn't matter. It can be added up at a later stage. For the time being, we say that, okay, we are looking at a certain hemisphere, and the radius of this hemisphere is some, say, capital R. Okay. And the direction where this phase center is the direction n cap. So this vector which goes, I should not have used. So let me remove this arrow from here if I can. Okay, somehow it is not working. Yeah. Okay, so this vector which goes from O to P, I can write as Rn0 cap. And if I, so this is the part of the sky I am sensitive to. And the source can be anywhere in the part of the sky. So maybe the source is somewhere there. And the vector that goes there will have this same magnitude, because as I said, everything lies on the surface of the sphere, but a different direction. Okay. Now, I choose for, see, when I try to write down the coordinates of the antennas, the coordinates of the antennas are all lying in the surface of the Earth. And even from 100-kilometer baseline, the surface of the Earth is more or less flat. We have to consider its curvature, but it's more or less flat. So if I want to write down the coordinates of the antennas, it's better to choose a Cartesian coordinate system. And the Cartesian coordinate system will obviously have the same origin as it here. And I choose the Z direction of the Cartesian coordinate system. Now I have to do an arrow along the phase center. So the Z direction of the Cartesian coordinate system that I'm going to choose is always along the phase center. And then I have X and Y. The X-axis is along east-west, and the Y-axis is along north-south. Why do I write east-west and north-south? Because I don't want to get into the right-handed coordinate system, which direction should I draw the arrow, etc. You should draw the arrow in the right direction such that X, Y, Z remains a right-handed coordinate system, and X is along east-west and Y is along north-south. Okay. Now, I have this X, Y, and Z coordinates, and any point in the sky I can now level in terms of the directions cosines of the vector that goes to that point. For example, this point, which I call, say, S, for the source. For this, vector will make an angle with x-axis, say, let's call alpha, with y-axis, say, beta, and z-axis, say, gamma. So I define the direction cosines. You know how the direction cosines are defined. So it's cos alpha. Okay. And the vector n cap that we have written earlier, I can also write in terms of L, M, and N. This you have seen already several times, where L square plus M square plus N square, what it should be? Anybody? Remember, n cap is a unit vector. All these n0, n1 are unit vectors. So what this should be?
1.
1, right? Unit vector. So this should be 1. So that one should remember. That actually answers one of the questions you had during Poonam's talk, but we will come back to it. What is N0? N0 doesn't have any projection on x and y. It has only projection along z, and that has to be 1. Okay, so this is the coordinate system that I choose. Now, if I have an antenna, so I have not put an antenna yet here. So say I have an antenna here somewhere. Okay, so I can put a vector to the antenna, and we'll call these vectors as vector x's. If this antenna is the antenna A, we'll call this xa. And now xa can have components along x, y, and z, right? What is interesting here is that you know that sun doesn't stay all the time in the sky, because sun doesn't move in the sky, rather Earth spins in its axis. So is all the sources. They never stay all the time in the sky. They rise in the east and set in the west. Most of the sources. Sometimes you will see some sources which actually stays 24 hours in the sky. You may think about it and try to figure out what will be those sources given the location of the Earth you are in. But the point is that the source position change in the sky, which means all the antennas that we are talking about here, the interferometry and the radio astronomy that we will be doing in this lecture, assumes that your antennas are always following the source in the sky. So if there is a source at P, at the phase center, as we said, your antenna will always keep that source at the phase center as it moves. Which means these components along x, y, and z of the vector xa will change with time. Because if the source is along zenith, if I imagine this my Earth, say the source is here, the antenna looking up, this is my xa. It has only z component because that is my z direction. When the antenna is here, the source, the antenna may have moved from there to there because of the Earth's rotation. The antenna still looks at the source. The xa vector is different. It should go from the center, but I cannot draw it there. So the xa vector is in this direction, and it will have different component along x, y, and z, right? So the components changes as the Earth rotates. Is the coordinate system clear? Is there any question at this point? Okay, so if not, let me proceed. And also, probably I started 10 minutes late, so I will eat up 10 minutes of the tutorial time. if probably Arnav will not fight with me for that. So this is the coordinate system. If you wish, you can take a screenshot of your screen, because this will be required. If you don't remember it, it will be required. I will try to keep it here. Okay, so let it be there. So let's see what we want to do. So given an electric field at the source, let me write the electric field at the source. Any electric field is E as a function of x and t. So the electric field at the source is E. I'm not using it as a vector. At this I called R1, this vector. So it's R1 at a time t. I want to propagate this electric field. I want to see that this is the electric field at the source. How is the electric field outside ionosphere? Why outside ionosphere? Because the ionosphere, I assume, is the first thing that will do any change to this electric field. So what is the electric field here? Well, for this, I can directly use Huygens propagation, as we discussed. The electric field just outside the ionosphere will be the following. Just outside the ionosphere, and see the ionosphere. So let's say that I have this antenna XA, right? So and the ionosphere is like maybe 10 kilometers ahead of before Earth. So the signal has to travel extra 10 kilometers from ionosphere to the antenna, but it has already traveled a lot. So we really don't care about those 10 kilometers. So I just say that the electric field at XA, but remember that is before the ionosphere. And I am trying to see what it is at the time t. So this is outside ionosphere. What will it be? If I now carefully write all the terms in that propagation that we are discussing, it's coming from an area, say delta R in the sky. So that small area that I have drawn there is, say, delta R. This is the Huygens factor that we are talking about. And then I have to write down the electric field at the source. In this case, is coming from R1. But you see, the electric field has traveled a distance dA. So if I measure it at t, that electric field should have originated earlier at this time. And let me write what is dA. dA is just the distance from R1 to XA. This distance. Okay, so this is the electric field that I expect to have just outside Earth's ionosphere. And this is completely coming from what we know about Fourier optics, and there is nothing more into this. It's just a result from the Fourier optics. Okay, so let me call it ion. So we have come up to ionosphere, outside the ionosphere. So let's go through the ionosphere now. So what happens now, if I look at this field, which is outside the ionosphere, and it's just above the antenna. So this is, I'm asking just above the antenna, what is the electric field? So this electric field, which I am writing here, still doesn't know about the antenna. But what will be this electric field? Well, we already said that the extra propagation of whatever 10 kilometers, will not talk about it. But what happens is that this is going through the ionosphere. This electric field is going through the ionosphere, and the ionosphere is not completely opaque to the radiation. So the ionosphere will do two things to this radiation. One is that it will add up a phase. The ionosphere. Okay, so let me take a step back. So if there is a propagation through any medium, the electric field, and the medium is optically thin, the electric field changes two ways. One is that its amplitude may get decreased, which is absorption, which does not happen in the frequencies of interest here. The other is that an extra phase can get added to the electric field. So that extra phase I write as phi. What will it depend on? It can depend on where the antenna is, because you can see that if I draw another antenna here, and this is the only ionospheric patch I have, and the source, the light is coming from that direction, it does not see the same ionosphere. So it depends on where the antenna is. It can depend on which direction the antenna is looking at. So if the light is coming from this direction, obviously the effect will be different. And it can also change its time. So that extra phase will be added up. There will be one more change. You see, the electric field, what we observe is a retarded electric field, so-called in terms of electrodynamics language. It's the electric field which is the observed electric field at T is an electric field which were emitted at dA by C time earlier. But this ionosphere, because it has a finite refractive index, the speed of light will be smaller in the ionosphere. So it will add up a delay. And the delay is just, you can consider as at a time delay, which can again depend on Xa and T. And it's essentially omega times tau I. So that is the delay. Omega is the frequency of radiation, if you wish. So what will happen to the E antenna A? The E antenna A will be E ion, is at Xa, position of the antenna A, times e to the I phi, and I'm not writing its dependences, e to the I tau I omega. Okay. Now, so far it doesn't know about the antenna. The electric field was traveling happily. Now it get to see the antenna, and the antenna takes away, or the antenna observes the electric field. So what does the antenna do? And that we have, Poonam had discussed. So what the antenna does is that it does not collect all the electric field. First of all, it collects the electric field only from that small patch in the sky. It may be a circular patch usually. I've just drawn it like that. But it also has directional sensitivity, which means that it will observe more from the phase center. It will collect more electric field towards the phase center. It will collect less electric fields from the sides. So what I will get here after the antenna is an addition of a receptor pattern of the antenna I am drawing it, I am writing it with a curly A. It can be actually a complex function. And this will be multiplied by, this will multiply this signal. So remember that this signal, okay, so let me correct myself a little bit here. And it's not wrong, but so this is different at different n. And the signal is also different at different n, obviously. So this is after the antenna. So when I say antenna, I mean the dish which is measuring the signal. Okay. And now, if you actually look at a dish, the dish is this collecting area. What it does is it takes all this radiation which is falling at different parts and sends them back to the focus because it's a parabolic dish. And there lies the receiver, which I call the dipole, which is a dipole, which is again, which can have a directional sensitivity, but let's say that all of those are included in the curly A. But it also has a gain. So given a certain amount of electric field falling on the dipole, it will record a number, right? And usually it records what we call voltages. So finally, what you get is a voltage at the dipole after doing all this at the antenna A at the position XA at time t. And as I said, that the electric field which is here after the antenna will be multiplied by a gain of that particular dipole. So that, which is also a complex number, can depend on the time. And then I have to put in all these things that I have been talking about so far. So let me get rid of this. So I have A, which is a function of n cap. Actually, it can also be a function of time. The antenna pattern can change with time. We'll see its implications. Then I have the ionosphere terms. Tau I is the function of the same things. I'm not writing again explicitly. Then the term before the ionosphere, finally the source. And all this is coming from a small area in the sky. So this is essentially an area. So let me also mention what this is. So this is r square times the solid angle, which I write as delta n cap. Okay. So this is what you get as a voltage at the antenna. There is a little bit more, which is a random number as noise, which depends on which antenna, may depend on which antenna. It's a function of time. Okay, so let's stare at this. So this is what I get at a given antenna as a voltage. This is one antenna. We'll record this, which has a gain of the dipole or the electronics. After that, it has a beam pattern of the antenna. It has contributions from the ionosphere, and it has the Huygens propagation from the source to the antenna. And there will be this noise term added. I'll put a hat sign here, which means that it's a random noise, which is usually again Gaussian random. Okay, so this is what we get. And we'll see that what to do with this in the next lecture. So I'll stop here about the lecture. So if you have questions, we'll go through those.
If you have any questions, please ask.